Hey guys, this is Ben again. I'm doing a video on complex numbers now. Hopefully you enjoyed the last video, the very noobish video on vector revision. Before we start this, I should point out that that vector revision video really is non-exhaustive. So there are many things that we did not discuss in there. For example, we didn't discuss scalar projection, dot product, cross product, all sorts of things, unit vectors, that sort of business. And the reason is because I've kept it bare bones so that we can just relate the basic idea of two-dimensional vectors to complex numbers. So without further ado, let's get into complex numbers. So I did say I would keep the drawings and text from the previous video and then just scroll down. However, I went to bed and turned the computer off, so it's now a new day and all of that drawing is disappeared. So we'll just do a quick rehash of what we talked about, and we said that you can have a vector like this, which would, if it's a two-dimensional vector, it's going to have an I component, which we'll call X, and a J component, which we'll call Y. And I like to use, actual numbers just so that it's easier for you to relate to. Sometimes the abstract gets a bit difficult to understand. So I think we used 3 and 2, and that was equal to 3i plus 2j, if you recall. And that meant 3 across 3i and 2j, where this was the vector A. Okay, so there's our mad minute on vectors, just recovered again. So how does this relate to complex numbers, you ask? Well, in complex number theory, we are using a similar idea, drawing a set of axes like this, and we are going to have a real one and an imaginary one. And so any complex number, why complex? Because it has multiple components, a real component and an imaginary component. So this is kind of analogous to the 2D vector situation because, and I'll just clear this now to free up some space. It is kind of analogous to our 2D situation because instead of having an I for what we normally call the x-axis, which in this case is called the real axis, instead of that we just have a complex number which might be z, right? Some complex number z, which is going to have a real component plus an imaginary component, which is similar to the idea of vectors because you're going to have this real component that heads you off this way or off to the left if it's negative, and the imaginary component which is going to take you this way or downwards if it is a negative imaginary component. And the difference is we could have a complex number like this where we have z is equal to 3 plus 2j, and the 3 is the real component. Notice there's no I here, right? We don't have any I. Sometimes you'll see an I in a complex number, but that's just used instead of j because it stands for imaginary. So the real part has no other no letters next to it, and the imaginary part has this 2j. And hopefully you can see how this is kind of analogous to the idea of a 2D vector. And indeed, in things like electrical theory, we will use complex numbers to represent things like impedance or currents, and that's because there would be things like phase angle. And you still get this resultant here, So if we had this being the 3 and this being the 2j, we would still have this resultant z, which is a complex number. Sometimes you'll see it with a bar over it like this, which just to indicate that it is a complex number. But you know, hopefully you're getting the basic idea, and the 2D vectors revision was sort of helpful in jogging your memory. Now this form here is called Cartesian form, because you know, if you don't know, this is Cartesian is referring to this guy René Descartes, who came up with this idea of representing things on a set of axes and visualizing problems in this way. So that's why this is called Cartesian form, because it very readily allows you to see the different real and imaginary components. You can also express a complex number like this. This would also be equal to saying, well, some magnitude of z at some angle theta. You can also represent it like this, and in this case the magnitude of z, if we just do a little bit of side working over here, so magnitude of z would be equal to 3 squared plus 2 squared square root, and hopefully that's familiar from the last video, which is going to be square root of 9 plus 4, which is equal to root 13. We could be more precise, not more precise, rather we could express this with a bunch of decimals, but we'd have to do some rounding, so I'll leave it as root 13. And the angle theta, which in this case is this bad boy here, and I appreciate this is not to scale, this very much looks like a you know, that these two sides are equals. I apologize, you just have to imagine that this vertical one is a bit shorter, I guess. So what's the angle? Well, you can solve for the angle pretty simply, just with a bit of trig, and I'll write a tan instead of inverse tan, just so you don't get it confused with some being raised to some power. Of opposite, which is 2, over adjacent, which is 3, and I don't remember what that is off the top of my head, and we are going to express this in radians. So what I'm doing right now is punching some stuff into my calculator. 0.588 radians. 0.588 rad. So what does that mean? It means that we can express this in terms of its magnitude and angle. So it would be root 13 at an angle of 0.588 radians. Right, and you could express it in degrees, but you know, for most of our maths, it does. You know, we're going to be dealing with a lot of fractions of pi and such, and so it does become quite helpful to have it in radians or in terms of a fraction of pi. So it's great when you do have a nice neat fraction of pi, I have to tell you. So perhaps we'll do an example as well that is a nice neat fraction of pi. Anyway, as this up here was called Cartesian, this over here is the polar form. Right, so now we've got two forms, Cartesian and polar, and you can switch between them. If you've got the Casio calculator FX991 ES that I mentioned in my last video, what you can do is readily convert between the two in the complex mode of the calculator. So you can just type in 3 plus 2i, it's I on the calculator instead of j. You just type in 3 plus 2i, and you can quickly convert to polar form, and it will tell you this information that we've had to sort of calculate manually. So what that means is it's really handy because you won't have to go through all of these steps, right? And you're allowed to use it in your exams because it's non-programmable, so yippee for you. Okay, so now you got an idea what a complex number actually is. This idea that it's got a real and an imaginary component. It can be expressed in a Cartesian or polar form. We should probably talk about modulus and argument. So whenever you hear these terms, and they're sort of fancy sounding, aren't they? Modulus and argument. Modulus of a complex number is literally this. It's magnitude, right? So this part right here, that is the modulus. Modulus. Hopefully I can spell properly. And then the argument is this other part here. That part is the argument. It's literally the angle. So, you know, if you get a problem where it's saying, oh, you know, you've got this complex number, it's given to you in Cartesian form, find the modulus of the complex number. Well, all you're doing is calculating the magnitude. So that should be pretty straightforward. You just use this law of cosines, specific case for right-angled triangles, and you'll be all set. I'll scroll down a little bit so that you can see it without getting rid of all of this, because it may be useful for you. I will get rid of this. Hopefully you've had a chance to scribble it down for yourself. Alright, so if we have two complex numbers, z1, which is equal to 1 plus j, and z2, which is equal to negative 2j. So first thing is z1, we've got a real component which is 1 and a imaginary component which is 1j, if you like. This j is on its own, there's one of them, 1j. This z2 is a little bit different, isn't it? We've got no real component and a negative 2j. So we could write this as 0 real component minus 2j, and hopefully that now looks a bit nicer for your brain to understand. And so let's go through some operations. Z1 plus Z2. How would we go about doing that? Well, all we do is we add the real components, so it'll be 1 plus 0, and then we add the j components, so it'll be j minus 2j, and then what we've got is we've got 1 plus, well, this is going to be negative 1j, so what I'll do is I'll just write minus j. 1 minus j. Well, that was pretty easy, wasn't it? So hopefully you see that all we're doing is we're adding the real components and we're adding the imaginary components, and it is dead set as simple as that. What if we wanted to do z1 minus z2? Does the same approach apply? Well, in fact it does. It'll just be 1 minus 0. So, you know, the real component of z1 minus the real component of z2 plus the imaginary component of z1 minus the imaginary component of z2. Now, don't get stuffed up by the signs. It's so easy to stuff up signs when you're doing things. Most of the errors I make are arithmetic ones. Get the hard stuff right and then stuff up the arithmetic along the way, and you end up with a bodgy answer. Anyway, we'll end up with 1 minus 0 is 1, so real component of 1, plus j minus negative 2. Well, the double negative just becomes a plus, doesn't it? So j plus 2j, which is 3j. Well, isn't that lovely? So same deal. We're just subtracting the real components. We're doing normal subtraction on the imaginary components. We end up here. So that's pretty easy, and hopefully the intuition for that is making a lot of sense for you. And you could then convert them to polar, as we've just previously described. But you know, Cartesian form is definitely easier for adding and subtracting. I find that anyway. When it comes to multiplying and dividing, well, that's a bit of a, so add or subtract, we'll put over here in this nice little box. And then what about if we multiply? Well, if we multiply, that's going to be a different situation, isn't it? We're going to have Z1 times Z2, and what does that equal? Well, the easier way to express this is by converting to polar form first. So in complex numbers, it is much easier to multiply complex numbers when they are in polar form. So all we do is we do it like this: magnitude of Z1 times magnitude of Z2, which you'll have if they're each in polar form, right? And then that's going to be at an angle which is going to be theta 1 plus theta 2. So you multiply the magnitudes and you add the angles. It really is that easy. So let's go through with it. Let's convert this one into polar. So the magnitude is going to be 1 squared plus 1 squared square root, so that's root 2, right? Root 2 at an angle of should be pi on 4. So yeah, pi on 4, good. Pi on 4. What about Z2? So we've got to put that in a polar form. So let's do that. We're going to have 0 squared plus 2 squared, because the negative, once you square negative 2, it doesn't matter if it's a negative, right? So you're going to have root 4, which is 2, and it's going to be at some angle. Now this one is interesting because remember it's negative 2j. So if we think of this in visually, what we've got is negative 2j, and that's it. We don't have any real component. So what does that mean for us? Well, it's pretty simple. All we're going to have, if we think of it in terms of, here's real, and that's 0 degrees, right? That's the reference. Always off to the right on the real axis is this 0 degrees reference, and we've got minus 90 degrees, because by convention going counterclockwise is in a positive angle, and going clockwise is a negative angle. Negative 90 degrees, which is equal to negative pi on 2 radians, right? So since we're working in radians, we're going to have this angle, which we don't even need to do any trig for. It's just going to be negative pi on 2 radians. So cool, no worries. Now we really have everything that we need to multiply, don't we? So if we go back down here and we say magnitude of Z1, which is root 2, times magnitude of Z2, which is 2, I'll put a little dot there so we know we're multiplying it, 2 root 2, and our angle is going to be theta 1 plus theta 2, so it's going to be pi on 4 plus negative pi on 2. So really we can just get plus minus, it's just the same as minus, so let's just put a minus sign in there, and we're nearly there. So we'll put the 2 out front. 2 root 2 at an angle of pi on 4 minus pi on 2. So pi on 2 is the same thing as 2 pi on 4, so this is pi on 4 minus 2 pi on 4. I'll write that there just so it's nice and neat for you. And so hopefully you can see that it's just going to be negative pi on 4. So we got one of this, and we're taking away two of it. If you think of pi on 4 as the something, we've got one of them, we're taking away two of them, we're going to have minus one of them. So it's going to be minus pi on 4. Cool. And well, we've done pretty well, haven't we? And remember, this is in radians, so as promised, you do have a nice neat fraction of pi here. And you can see how to multiply. So just a quick rehash. We wanted to multiply complex number z1 by complex number z2. We have done that by first multiplying the magnitudes to get the resultant magnitude, which is just here. We've done that, and it's 2 root 2. And then to get the angle, we've just added the angles of z1 and z2. So, you know, hopefully you can see that this is quite easy, and the best way to do it is definitely having it in polar form. The trap for you is just blindly applying inverse tan to try and calculate the angle. That is not the best way to do it. You really should draw a little diagram for yourself, as we've done here, because it becomes readily apparent that, well, we've just got this negative 2j component, and so the angle must be negative 90 degrees or negative pi on 2 radians. In fact, I'll actually leave that there for you, just in case you want to scratch your head over it for a little longer. So well, let's draw a box around our little multiply setup, right? We've now got that. Now we can do divide, and divide some stuff. So I'll make it so you can see those Z1 and Z2 definitions again before we start. So what if we wanted to do Z2 divided by Z1, and not Z1 over Z2, we're doing Z2 over Z1. We could do it the other way, but we're just going to do it this way because, you know, it's buckets of fun. Okay, so we've got Z2 divided by Z1. Is it going to be some similar idea to what's going on over here with the multiply? Is it going to be similar to this? Well, it is. In fact, we're going to simply do this: magnitude of Z2 over magnitude of Z1, and that's going to be at an angle which is going to be theta 2 minus theta 1. So when we multiplied, we multiplied the magnitudes and added the angles. Now we're dividing the complex numbers. We're going to divide the magnitudes and subtract when it comes to the angles. So that seems like it should be pretty easy. So what's that going to be equal to? We've already done the work of converting to polar, so we can just say that this is going to be so it's going to be 2 on root 2, right, at an angle of theta 2 minus theta 1. Now what was theta 2? It was negative pi on 2, so we've got that, minus pi on 4. And remember, we did this before where we said, oh, that's the same thing as negative 2 pi on 4, just so that they've got the same denominator, makes it a bit easier for us. So we've got negative 2 of something minus 1 of something, so we're going to end up with negative 3 of that something. So this is going to be 2 over root 2 at an angle of negative 3 pi on 4. And that's the answer. So that's pretty cool. So you got the basic operations down. You got add, subtract, multiply, divide. The world is now your oyster. Congratulations. So what else can we do? And what else is worth telling you about? So one of the things that I sort of assumed that any other people viewing this would know, so I didn't explain it, but you know, that's probably bad practice. I really should explain this, is that what is this whole J thing about? Well, what is J? j, or sometimes called I, is equal to the square root of -1. Right, that's what this is, square root of -1. So for example, why is this useful? For example, if we had something like the square root of -16. Can you take a square root of a negative number? You cannot. So there are no real roots to this, right? If it was +16, it would just be 4, wouldn't it? Square root of 16 is 4. However, with this minus here, you can't do much about it. But what you can do is say that this is equal to the root of -1 multiplied by the root of 16. So now you've got an interesting thing going on where you've got part of this you can solve, and you've got this j here, this root -1. So what we're seeing is we've got j times root 16, which is equal to j4, which is the same thing as saying 4j, right? Same deal. 4 times j, j times 4, same thing. So that's one of the useful things. And remembering this definition is very useful, because when you end up doing equations with different complex numbers interacting with each other and multiplying by each other, you might come across a case where j terms are multiplied by j terms, and so this is the same thing as doing root -1 times root -1. And a nice easy way to think of that is by, what is a square root? Well, it's just raising something to the power of a half, isn't it? So what we're doing is we're doing this, right? And when you multiply a base, you've got two things multiplied by each other, and they've got the same base and they're raised to some power. What we do is we add those together, which is equal to that base, and we add the powers, which is -1 to the power of 1, which is equal to -1. So j times j, this here, is equal to -1, and that's worth keeping in mind, because it sometimes becomes useful. The only last thing I would like to tell you is different ways that we can also express Z1 and Z2. So what we can do is we can also express Z1, this guy over here, we can express Z1 as a magnitude multiplied by some cosine of this angle plus j sine of the angle. And in our specific case for Z1, it's going to be, what did we find out? It was root 2 was the magnitude, and then cosine of pi on 4 plus j sine pi on 4. Now if you actually think about what is actually happening here, we're saying that if you have some complex number which we can represent as a vector, right, because it's quite analogous to vectors, Z1, this magnitude of Z1 here is the length of this line, this arrow. So if we then multiply that by cosine pi on 4, and remembering that cosine of an angle is equal to adjacent over hypotenuse, then what we're saying is that, well, it is this side adjacent, right, which is the real component, divided by the hypotenuse. So if we then rearrange this thing and we say hypotenuse, if we multiply both sides by hypotenuse, right, what we're going to get is they cancel out. Hypotenuse times cosine of theta is equal to the adjacent length of the adjacent side. And really that's what's happening. We're multiplying this here, this magnitude of this hypotenuse by cosine of the angle. And so what we're going to get is we're going to get the real component, the adjacent side. So what we can say that this adjacent side down here is going to be magnitude of Z1 times cosine theta, right? And we can say also that this side is going to be the J component. If you think about what's happening over here, we can say that, well, what is sine? Sine of theta is equal to opposite over hypotenuse. So if we multiply both sides by the hypotenuse, my writing's getting squiggly because I get excited, those will cancel out, and you'll get that the hypotenuse times the sine of the angle is equal to the length of the opposite side, where this is the opposite side, right? Here's the angle, here's the opposite side, and so this side here, that's what we're doing. We're saying, well, when we distribute this out, we're going to get the magnitude multiplied by this J sine pi over 4. So this is magnitude of Z1 times sine pi on 4 in the J direction. So hopefully you can see that when you express it like this, it really is like a Cartesian form of the thing, isn't it, sort of, because you've got this, you are defining this real and imaginary component pretty readily. But the useful thing about expressing it this way is you also have the benefit of the polar form, which is you have the magnitude readily visible to you, and you have got the magnitude of the complex number, so magnitude of Z1, and you also have got the angle readily visible to you. So this can be pretty handy. Anyway, I just thought I'd mention that with you before we move on. In the next video, we will talk about Euler's formula, and we're going to introduce an E term to all of this. Thanks for watching.